Welcome back. In the previous videos, we went through the theoretical foundations of control volume analysis. We saw that control volume analysis is a really good tool for analyzing conservation laws, such as conservation of mass, conservation of momentum, in control volumes. Control volumes are usually fixed regions in space. So these are volumes in space. It could be a room. It could be a cylinder in an internal combustion engine. It could be an airplane cabin, whatever that is. So it's a very good way of looking at conservation laws in these volumes of space. Now, you might be a bit overwhelmed with the theoretical foundations, but as you'll see, once we look at an example, that a lot of these concepts will become quite clear. So in this example, we're going to look at a nozzle. Okay, so a nozzle here is a contraction. So we have a velocity V1 on the left that is going through the surface A1. So this inlet, if we want to call it, it's not necessarily an inlet. This nozzle could be continuing over here. So recall that control volumes, control surfaces, things like that, they can be real or fictitious. So here we're just starting our analysis on this plane over here, which we call A1. Okay, so at location 1, we have an area A1 and a velocity V1. And at location 2, we have an area A2 and a velocity V2. And these upper and lower walls, these are solid walls. Okay, so there is no flow going through these. Okay, so the flow is only where we're seeing V1 and V2. All right. So in this problem, V1, A1, and A2 are known. And what we seek to find is an expression for V2, the velocity at point 2, given that we have a contraction from A1 to A2. And also, what is the force acting on the fluid from within the nozzle? So these could be viscous forces, they could be pressure forces, etc. What we're looking for is the net force, essentially. Okay? So what we can do is consider our control volume to be this internal volume within the nozzle. Okay. And it would actually really help just to formalize, especially this idea of these surface integrals that we saw. What we can do is split up our surface. So we have a control volume in red. And what we're going to do is that we're going to split up the surface. So we'll have one surface here, which we will call control surface 1. We can have another surface, control surface 3, and then we have the outlet, which we will call control surface 3. Sorry, so my numbering is off. Actually, no. Let's leave it the way it was. So we'll call this 3, and we'll call this 2. Okay. So I just separated the entire control volume into 3 control surfaces. So this is the inlet. This is the outlet, and these are the walls. Okay, so again, what we seek to do is find an expression for the velocity, V2, and an expression for the net force acting on the fluid. So I guess a good starting point is to see, well, what can we obtain from conservation of mass? Okay, so conservation of mass. So recall that it states that the time rate of change of the mass within the control volume plus this surface integral of the mass flow rate in and out is equal to 0. Now, again, the whole purpose of kind of blowing up this control volume into three separate control surfaces is to show the effect of this surface integral here. Okay, so let's express this surface integral as the summation of the integral on these three control surfaces. So that's pretty straightforward. So, we'll have something multiplied by ds plus something else multiplied by ds plus something else multiplied by ds. Okay, so we're just splitting this control surface, this surface integral, into three separate integrals. And this is all that this surface integral really is telling us, okay? So this surface integral just says that, calculate this integrand here over all the surfaces. So there is no reason why you cannot just separate them individually. Okay, so let's look at control surface 3. Control surface 3 is defined at the walls. So if we have a wall, such as this one here, okay, so let's look at our terms. We have a unit outward normal over here. And our flow, what is it going to look like? Well, our flow will likely be something like this, right? The flow is being turned in the direction of the general bulk flow, okay? It's also, walls are what we call impermeable, okay, which means that there is no flow going through it. So there's really two things here telling us that, well, nothing much is happening at this control surface in terms of how the conservation of mass will be dealt with. Okay, so a wall is known as an impermeable boundary condition. There's no flow that can pass through it. Okay, so therefore, intuitively, you can already state that, well, the wall will have no effect on the mass balance, which goes into the conservation of mass. Okay, so what we can say that the velocity going through control surface 3 is equal to 0. Okay, so there is no velocity going through the control surface. Control surface 3. There's no velocity. So this last term here, we don't need to deal with it. Okay. Let's look at the inlet. So that will be our control surface 1, the inlet. All right. So the inlet might look something like this. We have the velocity, which we call v1, and we have the unit outward normal like this. Okay, and again, these are always perpendicular to the surface. So again, as you can see in the mass fluxes, so the mass flow rates here, we have a v dotted with n, which will look like negative v1. And that's because the angle between v1 and n is 180 degrees. So the cosine of 180 degrees is negative 1. So it is just negative 1 multiplied by the magnitude of the velocity vector v, or v1 if we will. So that's just negative v1. Okay? So our term here for the integral control surface 1 of rho v1 dotted with n ds will be equal to negative of the integral control surface 1 of rho v1 ds. Okay? And so naturally, the dot product yields a scalar. That's why it's also known as a scalar product. So notice that I no longer have my vector notation there once I've carried out the dot product. If we assume that the flow is incompressible, so the density is roughly constant, or more importantly, the density does not vary over that control surface. Okay? And this is a common assumption that we will make. Then what we can do is, well, V1, well, let's write it out again here. So we have the negative of the control surface 1 of rho V1 ds. So if the density is constant, we can take it out. But also we're assuming that the velocity is constant over the entire surface A1. So what we're left with is negative rho V1, and the integral over the control surface 1 of ds. And ds is just a differential area, so the summation or the integral of all the differential areas will just be the total area. So we're just left with negative rho V1 A1. Okay, so hopefully that's pretty straightforward so far. So this here is how we're going to, so if I call this up here, this first integral, integral 1, then our integral 1 will be this term over here. Now let's look at control surface 2, which is the outlet. So at the outlet, we're going to have a velocity v2, and we also have a unit outward normal n. Okay, so the integral over the control surface of rho v2 dotted with n ds will be equal to, well, v2 and n are acting in the same direction. They are perfectly aligned, so there is an angle of 0 between them. So v2 dotted with n is just equal to v2. So we're just left with rho v2 ds. And this is evaluated over the entirety of control surface 2. And again, we'll make the same assumption that the density does not change and the velocity does not change. So we're left with rho v2 a2. And so this will be integral 2. So this will go into integral 2. Okay, finally we turn our attention to the volume integral. So the volume integral is the first term, which states that the time rate of change of the control volume of the mass within the control volume. Now, we've said that we're assuming that the density is constant, it's not changing with time, so that can also come out of the integral. So what we have is rho dv by dt. Okay, now this is the time rate of change of the volume. And this is the volume of our control volume. Now, the volume does not change with time. There's no reason to believe that this nozzle is somehow expanding or contracting. So this whole term is equal to 0. And this is very typical of incompressible flows. Okay, so we will see that for these steady type flows, this time rate of change will be equal to 0. Okay. So what we're left with, going back to our control or conservation of mass, so 0 on the left-hand side is equal to the time rate of change of the mass in our control volume, which, sorry, I'm just going to qualify this, really I want to drive this home. This is what we call a steady flow assumption. And I will further elaborate on this in a second. Okay? So, going back to conservation of mass, 0 is equal to the time rate of change of the mass in the control volume, which we've just stated over here is equal to 0, plus our surface integral of the mass flow rate in and out. So the first term will be the negative rho v1a1 plus rho v2a2. Okay. So we'll take a pause here. Well, first let's just rearrange it. So we have rho v1a1 is equal to rho v2a2. If you work out the units, you'll see that rho va, which you'll encounter throughout your control volume analysis study, is called a mass flow rate. Okay, so it has units of kilograms per second in SI, and we denote it by m dot. So what this is saying is that for a steady flow, the mass flow rate in is equal to the mass flow rate out. And this is a very important finding. And perhaps it is a bit intuitive, right? If we are saying that the time rate of change of the mass inside the control volume is not changing, it's equal to 0, there's no change in mass inside the control volume, then you would expect that whatever is coming in must come out. Okay? So that's not saying that the velocity in and the velocity out are the same, but this mass flow rate in and mass flow rate out are the same. So this product of the density, the velocity, and the area remains constant between the inlet and the outlet. Okay? So this is the mass flow rate, m dot. Now, we've said that the density doesn't change, right? The density is more or less constant throughout, right? We have an incompressible flow, right? We've set it up here, incompressible flow. For an incompressible flow, then the density at the inlet will be equal to the density at the outlet. So we can also state that V1A1 is equal to V2A2. Okay? So we can cancel out the density on both sides, so we're left with V1A1 is equal to V2A2. Now what does this tell us? For an incompressible flow, what we have, this is what we call the volumetric flow rate. And it has units of meters cubed per second in SI. And we denote it as Q, and that's very important. Okay, so a velocity multiplied by an area is equal to a volumetric flow rate. So meters cubed per second. So you've probably seen certain industrial equipment or something like that saying that it has a flow rate of, X liters per minute or something like that. That's a volumetric flow rate. So these two findings are very important. So for a steady flow, what we find is that the mass flow rate in is equal to the mass flow rate out. And this is this finding over here. Furthermore, for an incompressible flow, what we find is that the volumetric flow rate, Q, remains constant as well. So Q in will be equal to Q out. So two really important findings here. And we're very close to finding a solution to the first part of our problem. So recall that we were asked to find what the velocity at the outlet is. So we can just isolate that. So we can say that V2 is equal to V1 multiplied by A1 over A2. And recall, at the outset, we stated that V1 is known, and the geometry is known, so we know what A1 and A2 are. Okay, so again, the mass flow rate at the inlet is equal to the mass flow rate at the outlet for a steady flow. This we've shown here once we're setting this time rate of change to 0. A further assumption of incompressibility yields that the product of the velocity and the area, which is known as the volumetric flow rate, that too is constant, meaning that the volumetric flow rate in is equal to the volumetric flow rate out. Okay, and this is what allowed us to find our velocity at the outlet. So we've exhausted what we can usefully obtain from conservation of mass. Okay, our problem also asked us to find, well, what is the net force on the fluid? Okay, so we have some sort of acceleration probably of the velocity. So you have a velocity v1 and then there's a change in momentum. So there's a change in the velocity between the inlet and the outlet. What is the force that would cause that change in momentum? So that's what we're trying to find. So again, we have another conservation law, which will be the conservation of momentum, which states that the sum of the forces is equal to the time rate of change of the momentum in the control volume plus the surface integral of the what we call here the momentum flux. So how much momentum is being transported into and out of the control volume through these control surfaces, so the surfaces of the control volume. So as before, our dot product of V dotted with N will be equal to 0 at the walls, which is control surface 3. So this does not contribute to our momentum balance. Okay, so let's look at control surface 1. Okay, so that's our inlet. So as you recall from your study of dynamics, so this is a vector equation. We can split it up into different scalar equations. So let's look at the x direction. So if we say that this is positive to the right, then what we have here is control surface 1. So we're looking at just the flux terms over here. So we have rho v dotted with n ds. And so this will be equal to the density multiplied by v1. And then this will be multiplied by negative v1, right? As we saw in conservation of mass. And we can express this as v1 in the I direction. And then this will be multiplied by negative v1 ds. I forgot the density over here. And again, the same assumptions still hold. So over this area, there is no variation in the velocity, and there's no variation in the density. So these can all come out. So what we're left with is negative rho v1 squared. And then so we'll just be left with the integral of ds, which just gives us our total area A1. And all of this is in the I direction. Okay, so if we look at the outlet now, so again, we're going to assume that we are positive to the right, and our flux term will be, again, this is the general form, and then I'll make it more specific to our case over here. So we have rho V2 multiplied by, so again, you have V2 dotted with N, they're both in the same direction, and so we're just left with V2 ds. Okay, and note that I no longer have the vector notation because I've carried out the dot product, which gives you a scalar. Now, I can express this as rho V2 in the I direction, multiplied by V2 again, ds. And again, with the same assumptions as I did for control surface 1, where the density does not change over the surface and the velocity does not change over the surface, we are left with just rho V2 squared A2, and again, this is in the I direction. Okay, so let's now deal with the surface integral. The surface integral states that d by dt over the control volume of rho v dv. Now, what we're going to do is that we're going to make a steady flow assumption. So this assumption states that the velocity at any point in the control volume does not change with time. So although a different fluid particle can occupy the given point at different times, the properties of whichever particle is occupying that point will be the same at all times. Okay? So an individual particle, yes, it does accelerate, it does change with time, its velocity, its momentum. But if we consider a fixed point in space, that fixed point in space, which is occupied by different particles at different points in time, will have the same properties throughout time. Okay? So what this states is that the amount here, which is the amount of momentum inside the control volume, is constant, so that d by dt of rho v dv will be equal to 0. So this is a steady flow assumption. And this is often the case in many fluids problems. Okay, so again, it doesn't mean that there's no acceleration in the fluid. What this means is that there is no change in, if you were to query any given point in your control volume, then the properties at those points do not change with time. Okay? So let's go back and look at our conservation of momentum. So the sum of the forces in x is equal to d by dt over the CV of rho v dv minus rho v1 squared a1 plus rho v2 squared a2. And we've just established that this one here is going to be equal to 0. So what we're left with is the net force, which I'm calling the sum of the forces, is equal to rho v2 squared a2 minus v1 squared a1, and all of this is in the I direction. So I forgot my unit vectors over here. So recall that we found what the velocity at point 2 is in terms of the velocity at point 1. We've said that it's equal to a v1 multiplied by a1 over a2. So we can reduce the number of parameters in this net force. So again, I'll let you do the manipulations at home, but essentially just substituting for v2 squared, this expression over here, we end up with rho v1 squared a1 multiplied by a1 over a2 minus 1 in the I direction. And so this is the net force on the fluid. And this is what we were looking for in the second part of the problem. Okay, so this is the net force acting on the fluid that causes that change in momentum that we are seeing in the nozzle. Okay, so recall that we have different sources of forces that would cause this momentum change. So we could have pressure forces, viscous forces, body forces, but here in this particular case, we're just looking at the net force. So we haven't decomposed this force into its different components. Okay, so this was an application of control volume analysis. So we looked at a nozzle where we didn't know what the outlet velocity was, and that was part of the problem, as well as finding what the net force on the fluid is. Now, we applied control volume analysis, and what we did is that we separated the control volume into 3 control surfaces to really show that that surface integral that we used in our derivations of control volume theory, it can be just expressed as a summation of these integrals over the different surfaces defining the control volume. Okay, so from conservation of mass, we were able to find the outlet velocity v2. We also saw that a steady flow assumption tells us that the mass flow rate in is equal to the mass flow rate out. That is, there is no accumulation of mass inside the control volume. The further assumption of incompressibility, so stating that the density does not change with time or with space, then what we found is that the volumetric flow rate in is equal to the volumetric flow rate out, and that's given by the variable q. We then applied conservation of momentum to find the net force Fx, which causes the change or the time rate of change of momentum that we're observing. So hopefully this clarifies a bit how to apply control volume theory to real-world problems.